right. Okay, so let's start. Okay, so I've uploaded the lectures note to this morning in your e-learning. So I hope you can find that. Let me accept me dulu. Okay, for those who just joined, please scan the QR code first to record your attendance. Alright, so right. Okay. So let's continue. Since we already finished the chapter 3, I'm trying to finish the chapter as soon as possible so that we can do the revision more, especially on chapter 3 about the AC analysis. And after this, we're going to have OPM amp. Okay, so for today, we're going to learn about chapter 4 aja. Mana nak masuk? Okay. All right, so chapter 4, field effect transistors or FETs. Yeah. So for today, we're going to learn about the FET. Yeah, just a little bit about FET. Okay. Okay, and how it differs with BJT. Okay, macam mana FET ni is different with bipolar junction transistor. Okay, and then we're going to discuss the types of FET, and then we're going to focus more on Mosfet. Okay. Kenapa ni? There was a problem kejap ni. Problem with my presentation. I cannot see my slide kan. Kejap mana? Okay, this one. Kejap ni. Okay. Yeah. For those who just joined, kejap ni. I've got problem with my PowerPoint. Okay. Wait for a moment. Okay, then. Oh, by the way, your test 2 will cover until Mosfet, if I'm not mistaken. So test 2 nanti after we confirm the date, I'm gonna inform to you. Yeah? So, right. And also, it's already confirmed that your final exam we will conduct it online. So nanti be prepared for that too. Okay. Can you see my slide now? Can you see my slide now?
Yes.
Okay, I think no problem, yeah? Can see my slide. Alright, yes, betul. Okay, I need to accept. Siapa ni? Siapa ni ya tadi? Someone wants to join. Okay. Tak keluar ada notification ya. Kenapa? Nanti dia bunyi balik. Alright. So, today kita akan belajar, we're going to focus more about Mosfet. Okay, so because Mosfet yang going to come out in your exam. And then we're going to learn about the characteristic parameters and discuss and apply how the Mosfet. We're going to look into detail about the bias circuits. Okay, so let's start. So first, FET versus BJT. What's the difference between FET and BJT? Okay, so FET refers to field effect transistor. Okay, both transistor okay, for BJT bipolar junction transistor. But what's the difference? Yeah, so the differences between FETs and BJTs. BJTs is a current control device. Okay, current control device where IB, okay, current at the base, controlling the current at the IC kan, beta IC. Okay. Okay, so that's why we call BJT as current control device, and it has higher gains, yeah, higher gains. So, but for FETs, it is a voltage controlled device, okay, voltage control device. Okay, it's different. For this one is current, and this one is voltage, and then it has higher input impedance. Okay, it has higher input impedance, and then it is more sensitive. Okay, for BJT compared to BJT, FET is more sensitive. Yeah, and then it is less sensitive to temperature. Okay, tapi even though it is more sensitive, but it is less sensitive to temperature. So, if there is increasement or changes in temperature, FET is better compared to BJT. Yeah, and it is more easily integrated on ICs. It can be it can be easily to integrate FETs in a circuit compared to BJT, right? However, even though they have quite lots of differences, they have a similarities. Yeah, so their similarities is based on their applications. Okay, their similarities is based on their applications, where both of them can be used in amplifiers, switches, and also impedance matching circuit. So if there is questions asked, what is the difference and the similarities between FETs and BJT? So here are the examples of differences and similarities between FETs and BJT, right? So please memorize a few of these differences and few of the similarities, all right? So FETs, okay, what is FETs, yeah? So FETs, it is known as unipolar device. Yeah. So what is unipolar means? It is operates only in one type of charge carrier. So that is FETs. Yeah. So it is known as field effect. Why? Because the depletion region formed in the channel of FET as a result of voltage applied on one of its terminal gates. Okay. So FETs, usually they have three terminals. Yeah? They have three terminals, which is gate, source, and drain. Okay, so these are the three terminals for FETs. Yeah? Okay, so for BJT is different, right? For BJT we have collector, we have base, and we have emitter. Okay, so don't get confused between FETs and BJT. Kalau BJT we have collector, base, and also emitter. Okay, CBE. But for FETs we have G, S, and D. All right, so it is known as a voltage control device because voltage between two terminals, which is gate and source, will control the current through devices. Okay, so that's why it is known as voltage control device, because voltage between gate and source, okay, will control the flow of currents inside the device. So let's look into the types of FETs. Yeah? So FETs, we have several types. Okay, one is known as JFET. Okay, JFET, which is junction field effect transistors. Yeah? Okay, and then JFET also can be divided into two categories, which is N channel and P channel. Okay, and then another types of FET is Mosfet. Okay, and then Mosfet can be divided into two categories, which is D Mosfet or known as depletion. Okay? depletion MOSFET, or E MOSFET, which is known as enhancement MOSFET. Okay, so each of them have can be separated into two types, which is N channel or P channel, right? And then we have CMOS FETs, which is CMOS is combined. It combines N and P channel of E MOSFET. Okay, in a series, yeah, in series. Okay, so CMOS ni, it's combination of E MOSFET, both type, N channel and P channel, all right, in series. So it is known as CMOS. Yeah, all right. So for today, okay, for this chapter, okay, for this class, for this course, we will focus only on E MOSFET. Okay, we will not look for D and J FETs. We will not look on that, but we will focus more on E MOSFET, which is enhancement MOSFETs. Yeah, and all those examples, we're gonna look at N channel examples, right? So let's look the introduction of MOSFET. Yeah, so MOSFET, okay, MOSFET is applied. You can find MOSFET usually in calculators, in cell phones, in PCs, which are any device that use VLSI, which is very large scale integrated circuits. Okay, usually inside VLSI you can find this MOSFET. Yeah, so it contains hundreds to thousands of components that are etched on a single piece of semiconductors. Yeah. So the goal of integrated integrated circuit or IC, is to fit the maximum numbers of components in the smallest space. So the more components that you can integrate on the circuit is possible. Okay, so that's why MOSFET has been introduced, because MOSFET is very compact in size. Yeah, so MOSFET is okay, any temperature changes, and it has extremely low input current circuit. So with few amounts of current can run a MOSFET. Yeah? So it's required a low input currents. Yeah? So these are the advantage of MOSFETs. Yeah? So where is the applications of MOSFET? It can be used in 3-channel audio mixer, okay, silent switching, phase shift networks, and also motion detection system. So these are the applications of where you can use MOSFET. All right. So MOSFET, okay, MOSFET, even though it has quite lots of advantages, right? It is small in sizes, and then it has a low input currents, but MOSFET, yeah, is a very sensitive device. It can be damaged from electrostatic discharge. Yeah? So any form of electrostatics can damage the circuit inside the MOSFET. Okay, the configurations of MOSFET. So why? Because gate of MOSFET, okay, gate of MOSFET is insulated from channel, and the input resistance is extremely high. Okay, so since that the gate of MOSFET is insulated from the channel, so it makes the input resistance, yeah, the input resistance inside the MOSFET at the gate is extremely high, and this will damage the MOSFET. Okay, so this excess accumulate because the input capacitance combines with very high input resistance. Yeah? Input capacitance combined with this high input resistance, so it will accumulate, it will form a static charge, excess static charge. Okay, so what you should do, okay, what sound is that? Oh, any questions? Someone raise hand. Tak ada? Okay, so what you need to do when you are handling with Mosfet or you are working with Mosfet, so a few precautions that you need to be considered. So first of all, carefully remove Mosfet from its packaging. Okay, usually when you buy a Mosfet, okay, it is comes with a special foil conductive or a foam. Okay, to protect this MOSFET. So when you want to remove this MOSFET from its packaging, you need to be extremely careful, with when you want to remove it. So usually what we're gonna do is we will, if you are using hands, you should use holder wrist, assembler's holder wrist. That it's just like a strap, okay, at your wrist that were connected to the ground. Okay, so before you want to handle any MOSFET devices or usually any electronics components, you should strap your wrist with this assembler's holder. Okay, it's just like macam strap macam tu. It's just like macam gelang. Okay, it just around your wrist and then it is connected to ground. Okay, and the strap is connected to ground. So usually people, ya Allah, usually people, if you want to, we apologize for the inconvenience. People wants to handles with this device. They were going to use this. I have problems with my PowerPoint. Suddenly it's closed. Yeah, what happens? Wait, yeah, I'm gonna open my PowerPoint again. Okay. Share with screen. Present a window. Open this window. Share. Okay, so just now at this slide, right? Handling MOSFET. Okay, so next, other than that, what you have to do is you have to make sure that when all instruments, the metal benches used in assembly or test should be grounded. Okay, your table, your instruments, all of those tools should be grounded. Okay, and also before you want to remove the MOS device, okay, make sure that the circuit power is off. Okay, make sure that the circuit power is off. Okay, never remove the MOS device from circuit while power is on. Right, by fact, it is not only applied to MOS device. On all electronic devices, before you want to remove from the circuit, make sure that the power of the device is off. And do not apply signal to MOS device while the DC power supply is off. So make sure that the DC power supply is on, okay, before you apply any signal to the MOS device. Okay, so here are the a few of protections or precautions that you need to know, okay, before you handling MOSFET device. Okay, so I suggest that you also remember a few points from here, okay, because this might come out in your test or in your final exams, okay, for part A. Okay, so just remember about 1 or 2 or 3, okay, minimum 2 like that, maximum 3, okay, a few points so that you will not lose points for these questions. All right, so let's look at Mosfet construction and symbols. Okay, so E here is represent the enhancement, the enhancement mode. So E MOSFET, since that it operates only in enhancement mode, so that's why it is using the capital E in front of that. Capital E in front of that, So it operates only in enhancement mode. So it has no depletion and no structural channel. Okay, the substrate extends to silicon oxide or silica. Okay, this is also called as silica or silicon oxide. So these are the basic construction of E MOSFET. This is the drain. Okay, this is the gate, and this is the source. And the N channel. Okay, the N channel is the N type is located at the drain and the source, and this is the P substrate. Okay, so in this case, this is the N channel type. Okay, this is the N channel type. If P channel type, so it will gonna be another way around. So here we're gonna be P, and here we're gonna be N substrate. Okay, so these are the basic construction. So once you applied external voltage, okay, once you applied a voltage at the gate and source, so for example here, you apply a voltage here, so it will make the voltage at the VGS, okay, between the gate and the source here, okay, it will make a few voltage at the gate and source, and if the voltage value is bigger compared to the threshold, okay, when the voltage value at gate and source is bigger compared to the threshold, okay, so the MOSFET will on, okay, will on, and it will produce induced channel between the N dot region, between the N dot region. Okay, so this induced channel will form, okay, and it will and there is going to be electrons exist here. Okay, and this electron will attract to this positive channel, positive source here. Okay. Okay, and there will be a current flow. Okay, but if this VGS, the voltage at the gate and source is less than threshold, TH here refer to threshold. Okay, threshold. If the value of the voltage at the gate and source is less than the threshold, this MOSFET will not be on. Okay, it will be off. Okay, so there will no currents flow inside the MOSFET. Okay, so these are the construction of the MOSFET looks like, but in a circuit it will be described as symbols. Okay, so there is a conventional symbol and also simplified symbol. Okay, usually we are using simplified symbol rather than conventional symbol. Okay, so what's the difference? The difference is between these two arrows only. Yeah, the arrow here. In conventional symbol, the arrow at this in the middle here is separated with the source. But in simplified symbol, this arrow at the middle here is connected with source. Okay. So for N channel, you can see how to differ between N channel and P channel is by looking at the symbol here. If the symbol in the middle here, if the arrow, if the arrow in the middle here is pointed to the gate, okay, if this arrow pointed towards the gate, so it is N channel type. If the arrow, okay, at the middle here is pointed out, okay, it's faced out from the gate, it is the P channel type. Okay, so to identify between these two types, just look at the arrow here. Where's the arrow pointed at? Okay. So let's look how E MOSFET operates. E MOSFET operation in N channel. Okay, so we're gonna focus on N channel. So E MOSFET it is operating only in enhancement mode, as I said earlier. Okay, since that's why it is represent as E, right? It is operating at enhancement mode. So when at enhancement mode, the gate potential, okay, the potential at the gate must be positive with respect to the source. Okay, so gate and source here, it should be positive, right? So it means that if the gate and source is in positive, or the potential is positive, so it means that the MOSFET is in the enhancement mode. Okay, all right. So when the value of VGS, VGS is 0 volts, okay, there is no channel connecting the source and drain materials. So there is no channel, there is no a channel available here or created here. Okay, so it is separated. Yeah, drain and source are going to be separated, so there's no significant amount of drain current flow inside this channel, so it makes that this MOSFET is off. Okay, all right, so remember, yeah, when VGS is 0, so there is no channel created between drain and source. Okay, so there is no flow of drain currents inside this MOSFET. A temp file with the meeting. Oh, okay. All right. All right. So ID is 0 milliamps when VGS is 0 volts. Yeah? However, when ID is more than 0 milliamps, what will happen? Okay, when a positive channel is applied to the gate, okay, so G represents the gate, the N channel E MOSFET respond in the same manner as D MOSFET. Okay, as shown in figure, okay, when the positive gate voltage forms a channel between the source. Okay, so now the value of VGS is no longer 0. Okay, the value of VGS, it becomes positive value. Okay, so there will be a channel formed between the drain and source here. Okay, you can see that the N dot here is connecting between drain and source here. So by depleting the area of valence band holes, yeah, as the holes repelled by the positive gate voltage, that voltage is also attracting the minor carrier electrons in the p-type materials toward the gate here also. Okay, so these minor electrons, okay, these minor electrons will attract it to this, and some of this minor electron also will attract to the holes that have in the p-types here. Okay, p-dots here. So this form an effective n-type bridge between the source and drain. Okay, so this forms a bridge, yeah, between the drain and source. Okay, because of the the valence band holes and because of the valence band holes created during when we applied positive voltage at the GS here. Okay, so what will happen? It will connect the drain and the source here, and currents able to flow from drain to source here. Okay, so ID will be bigger than 0. Okay, when VGS is sufficient to form a channel. Okay, so when the value of VGS is increased, sorry, this should be lower, yeah? It should be GS like this, yeah? So when the value of VGS is increased, the newly formed channel becomes wider. Okay, this will gonna becomes wider and wider, allowing the ID to increase. Yeah, when the value of VGS decrease, the channels becomes narrower and ID will become decreased. So this depletion region is based on the value of voltage at VGS. So that's why FET is known. Okay, FET is known as voltage controlled device. Okay, because the voltage here, voltage at the gate and source, is controlling the currents inside the device. All right. Okay, next. So you can plot, you can plot the value of currents, value of ID currents against voltage of gate and source, where this graph is known as transconductance curve. So transconductance curve, or also known as transfer characteristic. Okay, it can be called either transconductance curve or transfer characteristic, either one. It is referring to the same graph, ID versus VGS, is shown in figure, and the primary differences are compared to the Mosfet. So all values of VGS should be positive, because Mosfet is working in enhancement mode, and enhancement mode requires VGS value in a positive conditions, right? So the point at which the device turns on, okay, the point that the device turns on is called the threshold voltage, or also can be signed as VGS threshold here. Okay, so it means that not when you applied a voltage here, it will create directly this depleted region. No, only if the amount of this voltage VGS is sufficient, only it will create this depletion region. So that's why you can see that this graph is not start at like this. Okay, because it will wait until the sufficient amount of voltage between the gate and source, then only it will turn on the device, the Mosfet, the Mosfet. Okay, so at the point where the currents flow inside the device, when it is called, okay, the voltage at the point that the currents flow inside the device is called the threshold voltage. Okay, so threshold voltage is the volts that turns on the device. Okay, so sometimes you can see that VGS threshold in some books it is represented as VTH. Okay, so VTH also refers to gate source threshold voltage. Okay, so it can be either one. It can, sometimes it represents as VGS threshold, sometimes it represents as voltage threshold, like this. Okay, so it depends on what kind of books that you refer. Okay, so summary of the operation of Mosfet. Okay, so it only operates in enhancement mode. So enhancement mode only will appear when the VGS is positive. Okay, when the VGS is positive. So when the VGS is increased, ID will increase, and VGS is kept constant here. VGS is kept constant and VDS is increased. VDS means that voltage between the drain and source. Okay, so when VGS is kept constant, VDS is increased, then the ID will saturate. Will saturate, and there will be no more increasement of currents at the drain, and the saturation level will reach. Okay, will occur at VDS. Okay, so VGS will reach if you keep constant VGS. Okay, it will make the currents at the drain become saturated, and once the current is saturated, the voltage between the drain and source also will saturate. So at this point here, is called the saturation mode. This is the saturation mode. Okay, saturation mode, and at this point here, it is called as ohmic mode. So this is just extra knowledge for you. Okay, at this point here, when it's still increasing, it is called as ohmic mode. At this point here, it is called as saturation mode. All right, and down here, It cannot be seen here, but it's actually a cut-off mode. Okay, cut-off mode. Okay, same as BJT. Okay, cut-off mode and saturation mode. But differ with BJT, here is called as ohmic mode. Alright. Okay, so to determine, Allah again. Wait ya. Wait my. Sekejap eh. Oh, I think because I didn't update. Sorry, wait ya. I think my PowerPoint still in a holiday mode. Okay. Alright. So this one. Share with present. Still in Raya mode. My PowerPoint, sorry. Okay, kejap eh. Mana slide tadi? Here. Okay. So to determine the ID when given VGS. Okay, this is the formula. No, Microsoft error reporting. Okay. Hi, again. Kejap eh. What happened lah with my this one? I'm using mana? Allah. Okay lah, I'm using the PDF one. Really? Open with PDF reader. Okay, this one. Okay, this one. All right. So present. Israel hack, yeah. Okay, so I hope not gonna be not a problem anymore because I'm using the PDF now. Okay, so yeah. Sudah slide yang mana dah? This one kan? Okay, so this one. Okay, you can see my screen, right? Can you see my screen?
Yeah, Sensei.
Okay, nampak kan? Okay. So to determine ID when given VGS, so ID equals to K VGS minus VT square. Okay, so VT here is represented threshold voltage. Okay, so as I mentioned just now, VT, some of the book use VTH, some of the book use VT VT. Some of the books use VGSTH. So in this formula, it is using VT. Okay, usually it's represented as VT lah. So this VT here is represents threshold voltage or voltage at which the MOSFET turns on. Yeah. So VGS, this VGS value lah. If you look at the graphs here, all right. So if you want to find the value of ID based on this graphs, okay, you can look here. When, for examples, yeah, when VGS is equals to 8, the value of ID is equals to 10. Okay, so from here, you can find the constant value of K, all right? So using this graph, okay, you can find the value of K here, right? You can find the value of K, where K represents a specific point of this MOSFET, okay? So K is always constant, okay? It will not change when the MOSFET is turned on or when the MOSFET is at the saturation point or in the ohmic point, okay? So K is always constant, yeah? So you can find K using any values of VGS here, all right? So K is equals to ID on divide with VGS. You just they just rearrange this formula, yeah, to find K. Okay, usually sometimes in equations K is given, so you don't have to find K anymore. But sometimes K is not given, but they're given this graph. So it means that from this graph you need to calculate this value of K. All right, so be careful. Okay, look at what information that you have inside in your questions. Yeah, so VDS drain source saturation can be calculated by VDS saturation. Sorry, VD saturation can be calculated by VDS saturation equals to VGS. VGS here means gate source, yeah, minus with voltage of the threshold, okay, or when the device is turned on, voltage when the device is turning on. Okay, so if you look at this graph here, so lots of information that you can find. Other than K, you can also find the value of threshold voltage. Okay, so threshold voltage in this, based on this graph, yeah, is at 2. Okay, 2. Okay, so these are the value of VT. All right, so VGS is values from any of this, yeah. So from here, you can also find the value of VD, all right? So VGS is equals to VT, okay? You will notice this for different reference book. And when ID is on, it's not always the same with VT or VGST threshold, okay? ID on can be at any values of VGS, all right? But VGS threshold is always the value of currents when they drain, when the device is on, right? So please note this as well, right? Allah tak ada tekan enter. Okay, so these are the summary of eMOSFET eMOSFET transconductance or transfer curve, okay, for N channel. So from here, okay, this value, okay, represents the ID equals to K VGS minus VGS threshold square, and this is when the ID equals to 0, and this is the voltage when the MOSFET is turned on, okay, and this is VGS on, ID on. Okay, yes.
Itu slide tak jalan.
Tak jalan?
Dia
Jalan.
masih dekat page 14 je.
Ya ke? Which slide
Sebelum
ni Oh, this one jalan tak? Yang ni
dah jalan.
Oh, okay. Oh, okay. Because I'm looking at the different. Oh, it means that I sharing the different one. Kejap I tukar jap. I tukar I share to you the wrong ni lah. Window je cancel. That. Hai, macam-macam hari ni. Okay, wait ya. Okay, now jalan tak? I'm moving the slide. Is it work? Is it move or not?
Dia berjalan.
Dia berjalan eh? Okay. Alright, so now let's look at this one. Okay, let's look at this part. Okay, so these are the summary of a Mosfet transconductance or transfer curve for N channel. So dekat sini you can find the value of ID from here, yeah. From this curve, you can find the value of K actually, yeah. The value of constant K using this formula, right? And then from this graph too, you can identify what is the threshold voltage for the device to turn on. And then from here too, okay, actually nanti you can draw the load line where we're going to look later on, yeah, how to draw the load line, and then at the cross of load line, tulis tak kat sini macam ni. I try ya. Oh, tak boleh tulis. Tak best sikit. Tak boleh tulis. Okay, tak apalah. Okay, usually dekat sini you can draw the load line. So daripada load line tu, from that load line, there will gonna be intersect dekat sini. There gonna be cross section between the load line and this transfer curve. So that cross, okay, is we're gonna represent a Q point from that. Okay, so we're gonna look later on. Alright, so let's look P channel pula, okay. So E-type MOSFET, this is just for your extra information. Usually in exam, they're gonna ask you N channel, but this is just extra information for you if they, for P channel. Okay, so for P channel, the opposite, the other way around with N channel. Okay, so if N channel, the graph is at the positive side. For P channel, the graph will gonna be at negative side. So it means that for the enhancement mode for P channel MOSFET, the GS, yeah, VGS voltage at the gate and source will be negative value, okay, rather than N channel. N channel, the gate and the source voltage value should be positive, but P channel, the gate and the source channel will be negative, yeah. So since that the value is negative, so the graph also, the transfer curve characteristic graph also will be in a negative side, right? So this is the, when you change the VGS value, so this is the saturation mode, this is the ohmic mode, okay? Please note, even though the voltage value of gate and source is negative, the value of currents, yeah, the value of currents is always positive, okay? Usually value of currents is positive. Kalau negative means that the direction of the currents is the other way around, okay? So for the P channel enhancement type MOSFET is similar to N channel except the voltage polarities and the current directions are reversed, okay? Alright, so these are the specification sheet that you can find if you buy a MOSFET dekat kedai, okay, in any store. Okay, it will comes together with this specification sheets. Okay, usually inside the specification sheet, there is information for the drain source voltage, drain gate voltage, gate source voltage, and all those things lah for you to refer. Okay, for you to, precautions for you for not to apply more voltage when you using this MOSFET. Okay. So these are the other examples of this specification sheets. Okay, so let's look until example 1 for today. For tomorrow, we're gonna go for FETs biasing. Okay. So look at this example 1. Okay, the spec sheet for the 3N171. Okay, so this MOSFET comes with the spec sheet, yeah, for 3N171. 3N171 usually is the types of types of this MOSFET. All right, so this one, yeah. And then they ask you the following minimum values are what IDS, which means that the drain source currents, the minimum value is 10 milliamps. When the VGS is 10 volts, yeah, and the value of VGS threshold is 1.5 volts. So using the ratings, determine the value of ID. Okay, they ask you to find the value of ID for the circuit shown in the figure below. All right. So, so first of all, what you need to do is you need to find the value of K. You need to find the value of K, the K constants. Yeah. So VD is given to you when IDS on, the value of VGS here, so, and also the threshold value. So you can easily find the K constants. Yeah. So K constants is 138.4 microamps over volts square. So from here, you can find the value of VG. Okay, VG, where is the VG value? VG value is value at the gate here. So here is the gate, kan? Here gate, here is drain, and here is source. So VG value is value of voltage or potential voltage value at gate here. Okay, so gate here. So VG is equals to VDD. Okay, why VDD? Okay, first of all, when you want to solve this, yeah, same as BJT, remove this capacitor. Okay, you need to remove this capacitor and also this AC source. Okay, remove this. So it will leave behind only this part. Okay, it will leave behind only this part. Okay, I cannot highlight, I don't know why. Try to highlight it again. Wait on, tak boleh. Okay, tak nampak kan? So it will leave it to you only this part, okay? Only this part, okay? Once you remove this capacitor and this AC source, okay? And also this capacitor and this resistor load also we're gonna be removed, okay? So once you remove all those capacitors and AC voltage, okay, you can see that this two, R1 and R2 is actually parallel connected to this gate, right? So same as BJT, okay, same as BJT. First of all, find the value of currents flow inside here, okay, sama je macam BJT. So the value of currents that flow inside R1 and R2, even though it is parallel, but it is same, okay. So value of potential voltage at gate here, same. I cannot draw, so that's why lah tak best sangat guna ni. Tak apa, jap. I try to use this one. I try to use this one. For here I can draw. Okay, I hope this will work. Sekejap. Window. Okay, I hope this will. Okay, kejap je. Alright, so okay, so look here. Okay, I'm sharing my slides now. Okay, so first of all, this part and this part you remove, yeah? You remove this part and it will leave behind only this part. Okay, so when it leaves that behind, okay, it will be, this is R1, this is R2, and this is the VG value, yeah, VG. And this is 10 volts. Okay, 10 volts here. Okay, this is R1, R2, and this is VG. Okay, so VG is parallel with R2, so VR2 is equals to VG. Okay, so if you calculate, you will get like this. Okay, all right. The currents, the value of currents is VDD over R1 plus R2, and then times with R2, you will get the value of VG. Okay, so the value is 5 volts. And then they ask to you determine the value of ID. So value of ID, currents that flow inside drain here, right? So ID using again the same formula. Once you know the value of K, okay. Once you know the constant value K, and then you also know the GS here, okay. VG here, okay, VG, because they ask you to use these ratings here, and then minus with this threshold, okay. So once you get this voltage value, right? So you can get the value of ID when the gate voltage is 5 volts. Okay, so this is the value of ID, value of currents that flow inside drain. Okay. All right. So we will stop until here for today. Okay. So for tomorrow we will look more into details, other examples of voltage divider bias and drain feedback bias. Okay, but we're going to focus more about voltage divider bias. So up until now, up until here, any questions that you want to ask?
Doctor,
Yes.
from this diagram, how to know which is the source and which is the drain?
Okay, which is the source and which is the drain? Usually, okay, usually the gate is here. The gate is always here. Up here is always source, and down here, up here is always drain. Down here is always source. Okay, it based on these symbols. It based on these symbols. It based on these symbols. Okay, up is always drain. Okay, at the side here is always gate, and down here is always source. Okay, it cannot be another way around, right? So the easiest part is to identify where is the gate. So when you can identify where is the gate, you can see that there is a line here, right? So this line is always next to source. Okay, the place where there is no line, here is the no line, so it is always connected to drain. Okay, so identify where is the gate, and then you can identify where is drain and source. But usually drain is up here, and down here is source, and here is always the gate. Okay. All right. Okay, so if there is no questions, we can stop here. Any more questions? For those yang datang lambat, for those who just join, yang tak sempat untuk attend QR. Alright, for those yang just join. Okay, if there is no questions, maybe we can stop here and see you tomorrow at 8. Yeah, and I hope my PowerPoint is okay on that time. Alright. Thank you. Assalamualaikum.